All right, that's good. Okay, so we're going to continue on what we did. First of all, I'll give you a quick overview. What we have been learning on Tuesday is we're trying to quantify bunch of the stuff we have known. First of all, we continue learning on the simply support beam, right? When you have simply support beam, you have force in the center, you have two resultant force on each corner, right? So left and right. So therefore, you will be half of the load here. So what we did before is we know distributed load will influence the shear force because integration of distributed load equals to shear, right? That's what we did. So therefore, shear force, if there is no distributed load, so therefore it's constant, and then amount of the shear force change will be influence the moment because integration of the V is M, right? That's what we have been learning. Now we introduce two more concepts, which is a theta and a y. By mathematical derivation, we know if you do integration of M, which is the shear, which is the bending moment inside, you get this thing called a slope. And lastly, if you do integration of the slope, you get the bending shape of it. So basically, if I give you a question like this, you should be able to give me 1, 2, 3, 4, all these 4 things. You should be able to tell me what's the shear force inside the beam, what's the bending moment inside the beam, and what's the slope of the beam, and lastly, what's the bending shape of the beam at any location, right? At any along the x direction. Make sense? We did this too before, right? I think 90% of students got a question 4 right? Yes? This is what you did, right? Forgot already? Oh man, I need to give you guys more surprise quiz. So you learn. How's that and the rest? You like it? All right. Right? This is what we did. So if you do integration further of this and this, then that's what you have. Why this is important? Because this tells you the slope of the beam at any location. Most importantly, this tells you deflection. So therefore, you know where the maximum deflection is and what's the magnitude of it, right? Okay, so what we're going to do is today we're going to go through hopefully 2 examples, but I think maybe you only have time for 1. But let's try to do 2. So let's use 2 examples to see how we can use this 1, 2, 3, 4, 5 equations to derive the shear force, bending moment, and the slope, and lastly the bending deflection of the beam. All right. Okay, so let's see here. My pen. First of all, I'll give you a very simple example. I should not even call it an example because it's a kind of like extension of the definition. Okay, so let's look at a very simple case. You have a simply supported beam sitting on a roller, right? And you only have y direction force, which in this case it's a distributed load, so distributed along the entire length. And you have an x and a y. Okay, so the quantity of this distributed load Q equals to 800 Newton per meter.
800 or 80?
80. Did I say 800? I'm sorry. 80. 80 newtons per meter. Okay. Now L equals to 20 meters. Oh, one thing I was trying to do is I was trying to update the notes on Blackboard. So there's 2 versions of notes already. I think the second version is pretty much up to date. And I gave the video to the department already. But the issue is each video is relatively speaking large. It's about 1.5 gig. So they need to break the video into small sections. So maybe 4 sections each. So they can upload that. So they're in the middle of uploading the video, right? And I'll keep you updated. Okay, so 20 meters long and 80 newtons per meter. So I'm going to ask you what is a shear force, bending moment, slope, and deflection. Okay, so these 4 things we're going to quantify. Okay, so like everything else, the first thing we do is free body diagram. So we're trying to see what's the resultant force on both corners. Of course, when you have a simple support beam, everything is easy. What you have is you just have to force on left and right. Okay, and let's say this is F1. That just equal to half of the total loading, right? And the effective loading of the beam is 80 times 20 divided by 2, which is equal to 800 newtons. Because the effective loading for discrete loading is kind of like in the center, right? It's exactly in the center, 10 meters to the left, 10 meters to the right. And the quantity is equal to 80 times 20, right? Okay, so that's what you have. And this F2 is equal to 80 times 20 divided by 2, which is 800 newtons as well, right? You have 800 newtons on the left, 800 newtons on the right. Okay, all right. So first of all, let's look at shear force as a function of distance. We know shear force is very easy, right? So here you have 800 newtons, and you have a discrete load of 80. So therefore, just look like this. And here is 800. Over here is negative 800. I didn't draw to scale very well, but you get the idea, right? Because dV divided by dx equals to q, which in this case is minus 80, right? Because all the shear force goes downwards. What are you looking at your computer? Do you need to use the computer to take the notes? Okay, can you turn it off? Yes? Okay. All right, so q equals to negative 80, right? So it goes downwards. That's what it looks like. Okay, x. So next, let's look at the bending moment inside of it. And the moment has a unit of Newton times meter. Okay, as we know, it should look like this. And when shear equal to 0, you have maximum for the bending moment, right? Okay, and at this point equals to the area of this triangle. What you need to do is this equals to 1 over 2 times 800 times 10, which is equal to 4,000. Right? So that's what you did. Okay, so the next thing is theta, which is slope. Okay, now slope, like we mentioned, is a also related to bending moment, which is one integration, right? So over here, we have shear force V. If you do integration, I just use INT, all right? Integration. You have a bending moment M. That's how you did it. And when you do one more integration on the bending moment, what you get is EI times theta. Now don't forget EI. I'll show you. Remember here. From here to here is just one integration, right? But here to here is also one integration. But be careful. Here what you have is M divided by EI. So therefore, if you do one integration for theta, it's not only theta, it's EI theta. Okay? All right, so in other words, EI, they're constant, right? E is Young's modulus, and I is a moment of area, so which is a constant as well. So constant, and then that's your slope. Okay, so Now, from this step from the bending moment to the slope, you cannot directly quantify them by integrate to calculate the area. Why? Because you have this, right? It's not only one integration like shear to bending moment. So therefore, when I didn't tell you what's E or what's the I, you cannot tell me what's value here because it's not only one integration. You also have constant in front of it. Make sense? Okay, but we can get a sense of how it looks, right? So what it looks like is this. Why is that? Now, it's because when you have a case like this, actually what you're seeing over here is you have equivalent load in the center, you have two supporting force on left and right. Now of course this is equivalent to have a concentrated force right in the center, therefore it look like this, right? Slope, what's the measure of slope? dy divided by dx, right? So at this point dy divided by dx is this, so therefore the slope goes downwards because slope is tangent of this angle over here. When it's more than 90 degrees, it's negative, right? Okay, so at the end over here, the slope looks like this. So therefore, this alpha here is less than 90, so it's positive. So it starts with negative, a huge negative number. In the center, it's 0, and at the end, it's positive. So here, this point, and this point, and this point is exactly the slope of at here, ooh, yellow is hard to see, and it's purple, and here. Right, so we look at these 3 points, it looks like this, so therefore this is the way it looks like. Okay, all right, lastly, is the deflection. Okay, we have deflection, of course we know it's going to be like this, and again from a slope to deflection, that's one integration, because if you look at this equation over here, from slope to deflection is just an integration, right? So there's no one of EI here, okay? So theoretically speaking, if we know the EI, you can also quantify the theta and the Y here. But in this example, I'm not going to do that. Probably next example or later on, I'm going to give you more complicated. Right now, trying to let you get the idea, okay? All right, so this is deflection as function of X. So of course, initially, this point is fixed. This is where the maximum is at. Sometimes we also call them delta max, right? Maximum deflection. It's in the center because this loading here is it's equivalent to a force in the center. Okay. All right. So let's call this is slope. This is deflection. Okay. So now, why we're doing this? Why this is important? Because when you design a material engineering system, especially when something is rotating, you want to know where the maximum deflection is on loading. Because when you have maximum deflection, chances are it might interfere with other components in the system, right? Especially take one example for a bridge, right? Usually in the center is where the maximum deflection is going to happen when heavy semi drives on the bridge, right? So you want to know what's the maximum deflection is going to happen. So therefore, when you design the bridge, there's something you can leverage, right? Okay, so we did that, and the next thing is we want to do a step further. So what if it's not only you have the distributed load? What if you have a concentrated force, for example, somewhere over here, right? You have two different kind of loading, which is very common for most of the mechanical system, right? So when you have combined loadings, how do we quantify all these four quantities? Okay, all right. So the next topic is on beam deflection by superposition. Okay, so first of all, what is superposition? Huh?
Some.
Yes, exactly. Yep, superposition is just a summation, right? Now, for most of analysis, we assume all the physical quantities can be superpositioned. Now, in theory, it means the effect of combined loading is equivalent to summation of the effect of each load. One of the simple example is this. Combined. Okay. So we have two forces applied on a small car which has a mass of m. Then I'm asking you what's the total acceleration caused by these two forces. What you need to do is you can say A1 equals to F1 divided by m. Oh, this thing here, combined. Where? Loading?
No, everything else is fine. Yeah, it's good.
Okay. So effect of combined loading is equivalent to summation of effect of each load, right? Okay. All right. So A2 is equal to F2 divided by m, right? So if we had two forces applied on the car and they're both going horizontal towards the positive x direction, A1 is just equal to F1 divided by m. A2 equal to F2 divided by m. And the total A is just equal to A1 plus A2, right? Or the total A can be just equal to F1 plus F2 divided by m. So by saying that, that tells you each load, they will have separate influence on the results, and then they don't influence each other. Okay, so here the assumption is it better if we do landscape so we see things more?
Sure.
Yes. All right. Assumption is number one, each effect is linearly related to the load produces it. So in other words, there's no nonlinear effect going to be considered here. Okay. And second,
To the load that produces it?
To the load produces it. So, for example, when you have 10 newtons, you cause 1 millimeter of deflection, right? And then you have 20 newtons, you cause 2 millimeter of deflection. So effect, for example, deflection can be one effect, right? And then the load produces it is a force. Make sense? Okay, so there's always linear relationship here, kind of like the acceleration, right? When the force doubles, the acceleration also doubles. Okay? All right. All right. here's important. A load does not create a condition that affects of another load. So in other words, let's still take the acceleration for example. That tells you no matter how big F1 is, no matter how small F2 is, they act separately, right? So, or vice versa, no matter how big F2 is, how small F1 is, they just act separately. So therefore, the load does not influence each other. Okay. Okay. So let's look at this example after we're clear with the assumption. Okay. So
Is this going to be a long example or a short example?
long, really long, mathematic intensive. Oh, actually, one of the things I forgot to mention is Society of Automobile Engineering (SAE), they are going to have a seminar on finite element analysis. Especially, I think they'll be focusing on using SolidWorks, right? So I know a lot of you have some issues for finite element using SolidWorks for project 1. So if you guys want, feel free to attend the seminar, right? And I can send you the information for the seminar, so you can go there, and then hopefully there'll be some good help for us for the future projects and also for future principal design, scene design. Okay, all right. So I'll send you the information. So pay attention. It's tomorrow?
Yeah, 3 to 4.
Okay. All right. At where?
I don't know about that one, but I can tell you.
Science studio.
Where?
The science studio.
Design studio?
Yeah.
Okay. Let me just quickly write it here.
Hmm?
3 to 4 p.m.? Is it? Okay. So try to be there.
This is here at ASIS. Yeah, that's what it says on the flyer. It says that it's at ASIS.
Where is ACES?
That's where we study.
Right downstairs.
Right downstairs.
Right downstairs? Okay, let me double check. Make sure I tell you the right information.
It's right here.
Okay, I can just take a look at yours. Can I see it?
See? What? What were you saying?
Yes. That's right. That's one. ACES. Who told me it's Design Studio?
Found it is.
Oh man, it's you again?
Nah, I wasn't even.
Okay, so okay, all right. So try to be there, right? It'll be helpful for sure if you want to know more about FEA. If you're not too familiar with FEA, so it's an ACES tomorrow. It's his date and 3 to 4 p.m. and it's about FEA seminar. Okay, so cut this. Let's try to move this thing up. Anyways. Yeah, because I gave them a seminar as well, so they are returning the favor. So, okay, so as shown in figure, you have a beam. determine the reactions and deflection as a function of x. Okay, so two things we need to do. One, determine the deflection. Second, determine the reaction. Second, deflection as a function of x. All right, so by the end of the example, you should know the deflection at any single point along the x-axis. Okay, again, it's a simple support beam. I'm just going to draw you the free body diagram of it. You have, of course, a distributed load. And in the y-axis, you have here a concentrated force F with a direction to the left of distance A and with direction to the right of B. And this distributed load has a magnitude of W, okay? W newtons per meter, right? And concentrated force right in the center. No, sorry, not right in the center. Right on the farther left side. Okay, you have R1 and R2, which is reaction force 1, reaction force 2. Okay, and the distance over here is L. So across the entire length, L. Alright, so this point we call it A. This point here we call it B. This point we call it C. A, B, and C, 3 points. B is the point where the concentrated force is applied. Okay? Alright. First of all, ask us to determine the reactions. Determine the reactions over here, which is a something relatively speaking easy. Okay, what we need to do is using the concept of superposition. Like we mentioned, there's two different forces, right? One, you have a distributed load. Second, you have concentrated load. Okay, so we consider them separately. Why? Because we can use the concept of superposition, right? Okay, so when you have a distributed load, let's say R1 prime is just equal to W times L divided by 2. W is the distributed load density, right? W amount of a Newton per meter. Now the total effective load will just equal to W times L, right? Because the distributed load is across the entire length from point A all the way to point C. So it's equivalent to a force in the center. So each of these two reactions will take half of it. So that's why it's called W times L divided by 2. Okay? Alright, and R2, it's the same thing. Another half, WL divided by 2, right? Okay, so I guess there's no question about that. For concentrated load, here's something different. This R1 prime, let's say this is the double prime means it's reaction force caused by the concentrated load. That just equal to FB divided by L, and R2 prime is F times A divided by L. Okay, that's exactly same way we did as before. What you need to do is you have a beam and you have two force, R1 prime, R2 prime, and F force in the center. Here's A, here's B. Right? You know how to solve for this, right? Summation Fy equal to 0. So this F equal to R1 double prime plus R2 double prime. And another condition you can use is summation MA equal to 0. This is point A, right? So F times A equals to R2 double prime times A plus B, which is L, right? You can solve for that. But anyway, so all right. So like we said, we're going to use superposition to discuss this, right? So the total R1 is nothing but equal to the two reaction force caused by two loadings. And R2 equals to R2 prime plus R2 double prime. That's how you do it. WL divided by 2 plus FB divided by L. And here is W times L divided by 2 plus F times A divided by L. Okay, so this is our answer for the first half of the question, although it's only about maybe 20% of the total effort, right? Okay, so do you have any questions about this to find out the reaction force on both ends using superposition? No? All right, good. So the next thing is we also consider separately because we want to find out deflection as a function of x, right? So let's look at something for a distributed load. For a distributed load, what you have is a over here you only consider this. And for concentrated load, you only consider this force. Right, you consider them separately. But now, what's going to happen is these two different kinds of load will cause different deflection of the beam. For this case, what you're going to have is your force here, it's going to cause the beam to deflect like that. So the maximum deflection is in the center. While for this, maximum deflection is at where the force is applied. Here's maximum, here's maximum, right? Here. Okay, so this is what it's going to be look like. So next, what we need to do is if we can quantify this y as a function of x, let's say y prime, this thing is y double prime as a function of x, then the total y is nothing but just superposition of these two. That's our approach, right? Yes? Right? Okay. All right, so this is our goal. Okay, we need to find y prime and y double prime. And the way we need to find is still we have a chain of command here, right? Once you find a v, you find an m. Once you find an m, you find a theta. Once you find theta, you find a y, right? So we do one step at a time. So first of all, let's try to see how we find a v. Once we find a v, then we can look for m by integration. Once we find out a m, we'll do one more integration to find a theta. Lastly, theta integration, then we'll find a y. That's how it works, right? And we're pretty confident we can find these first two. That's what we did before, right? Now again, this problem, the key concept is the superposition. So you consider these two cases separately and add them together, right? It's not too complicated, right? It's just two different loadings, so you have to do the superposition to add them together, okay? All right, so let's see over here. Now, first of all, for distributed loading y as a function of x, it looks like this. So it's going to be something like this, and it goes back. This is distributed load, right? And here we know the force over here and the force here. It's exactly in the center because this distributed load is equivalent to a force applied in the center, right? Okay, so the shear force looks like this, and the M we also know it's going to be something like this. It's highest in the center, right? That's something we already know. Now, the tricky part here is before, remember for question 4 the exam 1, all I asked you is what's the value here, what's the x-axis over here, what's the value here, and then what's the value here, right? 1, 2, 3, 4. It's only these 4 points I asked you for value, right? Now, see the question is asking for this. Deflection as a function of x. In other words, at the end, I want to know the value of deflection at every single x, not only these 3 points or not only this middle point. I want to know every single point value, right, for deflection. But like we mentioned, in order to find deflection, you want to get theta first. In order to find theta, you need to get m. In order to find m, you need to find the shear force V. So in other words, the first step will be we need to find out this, right? We need to find out at every single point what is the shear force. So therefore, once you do the integration, you'll know every single point of m, and at the end, you know every single point of the deflection y. Make sense? Yes? Confused? Yeah. All right. Okay, so let's continue over here. So these two I don't have to explain, right? You already know what's going on here and here. Okay, so let's do one step further. Okay, V middle point at the end. Something like that. Okay, all right. So I want to find out what's the V as a function of x, right? So for any of a straight line, I need to have 2 points to determine what's the line at any different x. In other words, for any straight line, I know this point over here, x is L divided by 2, y is 0, right? At this center point, x is L divided by 2, half of the length. Y-axis, which is the shear force, is 0. Okay, I also know this point. What's the x coordinates here? 0, right? What's the y coordinates over here? WL divided by 2, right? Because remember this, WL divided by 2, that's a this thing, right? So it's R1 prime. Okay, now on this line, I know these 2 points, so therefore I can derive the function of this line, right? The way we did is, remember, if you have a y, o, x coordinates, you have 2 points, x1, y1, x2, y2, and there's a line across it. I mean, can be a infinity long line, doesn't matter, right? So the way to find out what's the y as a function of fx is by doing this equation: y minus y1, y2 minus y1 equals to x minus x1, x2 minus x1, right? So you have 2 points. This is how you find it, right? Remember this? Yes, right? Okay. So, all right. So we can do the same thing for this. Okay. Now let's plug this thing in. So I'm going to use x and y to represent for x direction and shear force. All right. So in this case, shear force is my y. Okay. All right. So over here we have y minus WL divided by 2 divided by 0 minus WL divided by 2 equals to x minus 0, and you have x2 minus 0. Okay, in other words, what I'm doing here is I treat this is my x1, y1, this is my x2, y2. Nothing fancy, all right? This is all the thing I'm doing, and I just plug everything from here, right? Yes? Okay, all right, so we just plug everything in. Okay, the next thing is you rewrite this equation. So y minus WL divided by 2 equals to minus WL divided by 2 times x minus 0 divided by L divided by 2. Alright, so see here, my y is equal to this L over 2 and L over 2 cancels out. So minus WX plus WL divided by 2. Right? Okay, so all you did is just rewrite this equation, right? Oh, sorry, this might be hard to see here. Okay, so these two cancels, and you move whatever here to the right hand side. X minus 0 is just leave with x, so don't forget your negative sign. And that's it. Okay, so we agree this is expression of y as a function of x when you have a straight line, right? Okay, now what did I say initially? What is my y at this moment? What is the y? Huh? What is the y?
Right?
Huh? Yeah, that's my shear force, right? X is still along the x coordinates. My y right now at this moment is my shear force, right? Because I'm trying to derive a shear force equation. Although this is supposed to be a straight line, I didn't draw it too straight, huh? All right. Had too much coffee today, sorry. Hands are shaking. All right. So that tells me my shear force is derived by this equation. Okay. All right. Let's do experiment. Let's try to plug a couple numbers in. What if you plug x equal to 0? X equal to 0. So shear force equal to WL divided by 2. So that tells you when at x equal to 0, shear force should be WL divided by 2. Ooh, which is right, because this is exactly what this point is about, right? X is 0, WL divided by 2. All right, so what if you plug in y equal to 0? So if y is 0, so therefore x equals to L divided by 2, right? Okay, so that's right. Because when you look at here, when x is equal to L divided by 2, y is 0. Okay, so now we find the exact expression of shear force as a function of x, which is this equation over here. Okay, we treat these as the only resources we have to find y. Okay, all right. Any questions so far? Okay. All right. So if we don't have any question, the next thing is a remember this. When we have a shear force, if we do integration of shear force, then that is my m, right? Okay, we're good on that. Now, one other thing I need to remind you here is this. All right. Okay, by looking at this equation,
Sir,
bunch of yes.
all that is just with a distributed force?
Yes, exactly. We only consider distributed force because all we are doing now is looking at distributed force. So this is a shear force expression. We have distributed force, right? The concentrated force we have not even considered. Okay, so good. Let me just try to write it here. Consider only distributed force, all right? So this is what we have. So the concentrated force will deal with that later, okay? All right, so let me see. I'm trying to remind you here. There you go. Okay, so eventually we want to get a y, right? Okay, so we know only look at the left-hand side of the equation, all right? Only look at left-hand side because right-hand side is easy. Integration, 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 right? So from the left-hand side, you see here the shear force has some coefficients, which is 1 over EI, which is a constant, right? And over here, M has a coefficient as well. And then theta doesn't. Why doesn't? Because when you do integration of M over EI, that's where theta is coming from. So let's just save some time and do us a favor. Let's just consider these coefficients first. We agree on that, right? Okay, so what we'll do next is we have the 1 over EI directly. Okay, so we'll treat these coefficients. So what we didn't know also is when you do integration of that, this is theta. And you do one more integration of theta, is your y. This is the ultimate trace of what we're going to do next, right? We'll have to do 1, 2, 3 integrations. Yes, with the consideration of these coefficients. All right. Sorry, this is EI, not E2. Okay. Looks like I'm making you guys nervous, huh? Looks like everybody's going in and out. Yeah. Okay. All right. 3 times of integration, right? We agree on that. Okay. So we have 1, 2, 3. 3 integrations. Okay. So we know this v here, which is what we exactly did, right? Minus wx plus wl divided by 2. 3 integrations. Now, this is exactly our y. Agree? With the consideration of the coefficients, like we mentioned, do 3 integrations of the shear force v. That's exactly our y. Okay? All right. Okay, so when we have 3 integrations, then we have to consider things separately, one after another, right? So first of all, you do 1 integration, 1 over EI. You have integration, integration Okay, so minus Wx, if you do integration equals to z, right? X squared divided by 2 plus WL divided by 2. This is constant, so therefore once you do integration, it's x, right? Okay, we're not done yet, right? Because remember, and anything else? Yes, we have to plus a constant, right? Because once you do the inverse, it should be able to go back to x because derivative of a constant is 0, right? So when you do integration, don't forget this constant. So let's say this is constant m. Okay, dx, dx. Although it's complicated, but we're one step closer to the final answer. Okay. All right. I don't really like this constant because I don't know what's the value of it. I know w, I know x, I know l, right, which is all given. But m, I don't know. So let's try to get rid of it. Okay. So now, who can tell me what's in these parentheses? Physically, what does it mean? Inside these parentheses. Yes, that's a moment, right? Excellent. So moment we know for distributed load, you have shear force going this way, moment going this way, and then the theta goes this, and eventually it goes this, right? So Vm, theta, and y. This is what we learned. Okay. For moment, this is moment. For moment, when x is 0, what's the y value here?
0.
It's 0 as well, right? Exactly. So if I plug x equal to 0 in it, whatever inside the parentheses should also equal to 0. Agree? Because the moment at the end is 0. Okay, so we plug in 0 over here. This becomes 0. This becomes 0. So therefore, m is 0. Get it? All right, good. Okay, so therefore, what we end up have is this. One step closer. Okay. All right. So let's keep on doing the integration. When the vi integration, we know x squared will be x cubic divided by 6. Let me just write 2. 2 times 3 plus WL divided by 2, x divided by 2, squared divided by 2. And also, of course, you have another constant. Let's say that's another constant n. Right? Okay. Now, whatever inside this parenthesis, let's not consider the coefficient 1 over ei here, right? Whatever inside this parenthesis is what? Huh? It's a shear? Who said shear? Yeah, it's slope, right? We're not going backwards, right? We're going forwards, right? So this is slope. Exactly. So slope, we know a special point as well, which is L divided by 2, 0, right? Because in the middle, the slope is 0. Okay. So if you plug in x equal to L divided by 2, whatever inside the parenthesis is 0. Okay. Now, let's see here. You can do the calculation. I did that. Unfortunately, n is not 0. So, yeah, left a mess for us. WL cubic divided by 24. Okay. All right. So what we have now is minus wx cubic divided by 3, nope, 6 plus WLX cubic divided by 4 plus WL 3 divided by 24 dx. All right, so let's do one last one.
You're not doing that on purpose, right? All your L's are just L's. Sometimes you write them capitals.
Yeah, I'm sorry. I'm not consistent, huh? All right. L. Which one do you guys like? This or this?
Lower one.
That? What's that?
Second one.
This one? This? Okay, okay, I'll try to change it. All right. So I'll change it so therefore it'll be more consistent. WL L. And the I is terrible too, huh? Okay, so one step. We have one last step to do here. All right, one more integration. Over here, you have minus W x of 4 divided by 24 plus W L 3 times divided by 12 plus W L 24x plus whatever the constant, let's say P is, right? Okay, this is our final answer for y. Don't forget what's inside these parentheses here is my y, right? Is my deflection. And for deflection, I'm just going to draw it here. X, y. When x is 0, y is 0, right? So plugging x is equal to 0, whatever inside the parentheses should be 0. So therefore, good. P is 0. Okay? All right. So, good. We have that. The next thing is I am going to rewrite this final expression a little. EI minus WX of 4 divided by 24 plus WL all right, so this is our final answer is, and there's one more thing you can do is over here, huh? Okay. There's one last thing you can do is don't forget one thing. All we have been doing is on the right hand side of the equation, right? See over here. It's all on the right hand side of the equation. What's on the left hand side? That's y, right? That's exactly what we have been looking for in the past 10 minutes. So don't forget that. This is your deflection when you have a distributed load, right? Okay, and we can rewrite it, make it look a little nice because I don't really like negative coefficients for the first components. So, and also there's W across all the element. So you can have WX divided by 24 EI as your coefficients. Then the inside of it will just be 2 times L x squared, which is my second term for the above, minus x cubic minus L third. Oh, sorry, plus. All right, so that's what you have. Okay, so this is exactly what we need to look for. Remember, what is this question asking for? deflection as function of x, right? So this is distributed load cause of deflection. And remember what I said? So we're halfway there, right? Yes, we need to look for the other. So the other is caused by concentrated force. So this is a very important example, okay? We'll be seeing it in exam. We have concentrated force. What we have is similar, right? Let me first of all give the overall picture of it. So you have shear force goes like this. This is your shear force, and then you have your moment, which goes upwards at a maximum, and then goes up. This is your moment. Also, you have your theta, which goes like this. Right here passes through like that. Ooh. This is my theta. Now lastly is my deflection. Okay, so it's my deflection. All right. So this is the overall idea of it, right? This is what it looks like. So what's different about this is we have two different sections. First of all, you have in this section equal to B, in this section equal to A. That's what we know, right? The geometry of it. So therefore, when you consider this, some big problem is going to happen. What's a big problem? Remember, when you have distributed load, what does a V look like? It's a straight line, right? Okay, for a straight line, of course, I can find this continuous. There's no discontinuity along the line. Uh-oh, I have a big issue here. Houston have a problem, right? What's the problem here? At this point, it's discontinuous, right? When you have discontinuous, there's no way you can write one function to satisfy for all, right? So your V will be equals to f1x or equal to f2x. When x is smaller than a, well, here is x bigger than a, right? Because remember, here the distance is a, here the distance is b. Agree? Right? For the shear force is discontinuous, so you have to have two different sections instead of one. So therefore, all your M will have two different sections. You have M1 and M2. And your theta will have theta 1 and theta 2. And your Y eventually will have Y1 and Y2. And which is divided by with X is smaller than A or bigger than A. Make sense? Right? Yes? So there's two lines here. Okay? Alright, so I'm not going to repeat what we did for the integration. You can do that if you're interested in that, right? I'm just going to write out the final answer. So of course, overall is when x is bigger than 0 but smaller than a, you have y1 equal to integration of your v1 dx dx dx, and then when x is bigger than a but smaller than b, your y2 is equal to integration v2 dash, right? Okay, So you can repeat what we did. Actually, if you want, it's relatively speaking easy. Why? Because this V1 and V2, they're constants, right? This is my V1, and this is my V2. So when you do integration of a constant, relatively speaking, that's easy, okay? But although you have x again. All right, so the answer, I'm just going to write it out. Y from point A to point B. FBX 6 E I L x squared plus b squared minus L squared, and y BC equals to F times A L minus X 6 E I L x squared plus a squared minus 2LX. Okay, now we know why it's two sections, right? Because it's discontinuous force. All right. Okay, so this is what we end up to have. All right. So, well,
What did it say? Right? Oh, 2L.
huh?
Oh, never mind. I see.
Okay. If you want, for those of you who had the textbook, and I'm sure most of you will have an electronic version of the textbook, right? If not, just Google it. It's somewhere. And don't tell them that I told you to Google the book. Because they want to sell the book. They asked me what textbook I want to use, and I gave it to them. They're supposed to make some money out of you guys, but I don't want you. I don't want you to pay for a fortune to buy the book, right? Anyways, the shortcut of this is the reason why I say it is on table appendix A9. You can find it, all right? Or another way you can do is you're supposed to write this in your cheat sheet because all these equations are important, all right? Okay, so good. We still have about 8 minutes. So
What you're saying is that it's always going to come out the same, according if it followed that format originally.
yes, if the question I gave you, because the reason why I gave a very specific, a very general question here. See here, I didn't tell you what's A, what's B in quantity, right? I just give A and B. And also, I didn't tell you what's W. I just give you a W over here. So I just want to make it generous. No, generic. All right. Okay. Okay. So remember, we have this. Right. Now we solved for this, and I just gave you this, or you can find it from the back of the table. All right. All right. So once we do superposition, let's add two effects. Caused by two loadings together. We have concentrated and we have distributed. Okay. All right. So in this case, y AB equals to FBX divided by 6 EIL x squared plus b squared minus L squared plus WX 24 EI 2L x squared minus x cubic minus L cubic. All right, so YBC, it's the same. FA L minus X 6 EI L x squared plus a squared minus 2L x plus WX 24 EI and 2lx squared minus x cubic minus l the third. All right. Here and here they are from discrete load, while this section and this section is from concentrated load. Right? Okay, so all you need to do is just add them together. But unfortunately, for concentrated load, the function is not continuous, so there's no way we can have one equation for all. We have to have two equations for different cases. Now remember, here is this. Right? That's a condition of this two. Depends on your x. Okay, we'll solve for the question. What's deflection as a function of x? Okay? So therefore, at any location, we can automatically know what's the quantity of the deflection. Yes? All right. Okay, any questions? Yes?
How do you find where the maximum deflection is combined? Once you have the actual, the distributive and the concentrated,
Uh-huh.
how can you find where the maximum deflection is?
How do you find it out? Okay, then you have to, there's two ways you can do. So we have two functions, right? YAB, which is a function of x, and then here we have YBC, which is also a function of x, right? What you can do to find out maximum value is do derivative. When your derivative is 0, that's your maximum, right? And you do the same thing here. When you do derivative, you find out your maximum. Because remember this? Yeah, if your deflection is not a single function, what it end up to have is, for example, it looks like this, and that. So y, x. How do you find a minimum or maximum value? You do derivative, right? Because when slope is at a 0, you have your either minimum or maximum value, right? Yes? Okay. So you find an x and then you plug it in to find a y and then compare it to see which one is bigger. And that's how you find an answer. Okay? Make sense? So whenever you have a function, if I ask you to find a minimum or maximum, you always do derivative. Once you have derivative equal to 0, slope is 0, that's your maximum happens. Right? Okay? Or minimum happens, in other words. Right? For example, you have a function like that. Here is slope is 0, here the slope is 0. Right? You have your minimum and the maximum. Okay? Alright, good question. Any other questions? Nope. Alright, okay, I'll see you guys in 2 days.